Welcome back to our third and final segment of, investigating the factors that affect the magnitude of the electrostatic force between any 2 point charges. This is with respect to the Coulombs law, as you'd know it. Now we have managed to look at how, the product of the charges affects the electrostatic force. Now let's change our gears and look at the distance between any 2 point charges. How exactly does it affect the magnitude of the electrostatic force as suggested by the Coulombs law? Right. Now, we have a scenario here which says predict what happens. So it's all about predictions. Predict what happens to the magnitude of the force. So the electrostatic force in this case still remains our dependent variable. We're going to change the distance between the charges. Now the distance is our new independent variable. In other words, so the magnitude of the charge will remain constant, right? The only thing that we're changing is actually the distance, right? Now, we've got 2 point charges, Q1 and Q2. Each of magnitude, Q1 is -1, okay? Q1, if we can collect our data, Q1 in this case is equals to negative rather, okay, that's negative. Let's correct that, right? So Q1 in this case is given as -1 microcoulomb, okay? While Q2 in this case is a +1 microcoulomb. So these are essentially opposite charges, right? So in other words, there is an electrostatic force that exists between them, and the distance between them it is measured from those two imaginary lines is actually 3 centimeters, okay? So we'll change the distance while keeping these two the same, and we want to see how it affects the magnitude of the electrostatic force, right? Now, in the table of results, you can see that the distance is what is changing while both charges remain constant. So the product Q1, Q2 is controlled, okay? Why are we saying that? It's because we're not changing the magnitude of the product of the charges, or either we're not changing the magnitude of each charge, which actually affects the product anyway. But now what is changing here is our distance between the two charges. So this distance R is actually our independent variable, right? So by changing R, we want to see how it affects the magnitude of the electrostatic force that exists between Q1 and Q2. So if we go back to our previous slide, you'd realize that the force is given when the charge is -1 and +1 and the distance is 3 centimeters, the force is actually 9,9, which is approximately 10. So this is what it says here. But if it's 2 centimeters, it's going to be that. Let's actually go to our simulation and check what happens if it's actually 2 centimeters. So 2 centimeters, very careful about that. I'll put Q1 there on the 0 to make the measurement easier. Okay, there is the force. Okay, there is the force. I must change this one to -1. Okay, Q1 must be -1 microcoulombs, while this one becomes +1. And let's see how it affects the force. So the force is actually 22,46, right? So this is what it suggests. If we go back to our table, this is the actual force that the distance is 2 centimeters, okay, while the force is 25,9. And then when we increase the distance between them to 3 centimeters, let's see exactly what happens. So the force is affected by distance, okay? So the distance must be 3 centimeters now. What exactly happens? There is the force. Now the force is 9,986. We have made the distance 3 centimeters between Q1 and Q2, right? So that is 9,9. So if we go back to our table, this gives us 9,9, okay, newtons, right? So there's a decrease there. What if we make the distance 4 centimeters? Let's see what happens. Okay, if we go back to the simulation, Now the distance must be 4 centimeters. I think we can almost predict. Now it's 5,617. Okay, we go back, 5,617. Okay, 62. Okay, newtons. I think you can immediately pick up the trend. The greater the distance between the charges, the lesser the force becomes. Okay, are we on to something? Now let's make the distance between them 8 centimeters for argument's sake. Okay, if we make the distance between them 8 centimeters, let's move these around so that we create space. So that's 8 centimeters. We take this one there. Now it's 1,4 newtons. Okay, even smaller. So we go back to our table, 1,4 newtons. Now, what's the pattern that we are getting here? As the distance between the charges gets bigger and bigger, how does it affect the force? The force gets lesser and lesser. But let's pay attention to the proportion in which the force is decreasing while the distance increases, right? So if we move forward, the question says, what happens to the force when the distance between the charges increases? We know that the electrostatic force decreases, okay? So the electrostatic force decreases. Okay, there's a decrease in the electrostatic force. But if we decrease the distance, so it means if we go back, here would say moving upwards from 8 centimeters to 2 centimeters, what is happening to distance? Distance is actually getting shorter and shorter. What's happening to the magnitude of the electrostatic force? It's increasing. So we can safely say that if the distance between the charges, the electrostatic force will increase, right? So the electrostatic force between those two charges increases, right? Are we on to something here? Because we are worried about the mathematical relationship in terms of the factors that affect, the magnitude of the electrostatic force. So this is the gist of exactly what we want to discover or arrive at. Right, now here is a graph that shows exactly what happens, okay? So it says here what happens to the force when the distance between the charges changes, okay? Now we are saying here, the mathematical relationship, we are saying that the electrostatic force is inversely proportional to the square of the distance. So if the square of the distance increases, what happens to the electrostatic force? Let's check that. So this is a smaller value of r squared. It means there is a shorter distance between the 2 point charges. There is the magnitude of the force. What if we make the square of the distance between them greater? What exactly happens? You'd realize that if let's say this is F1, okay, and then that is F2. What are we saying exactly? If the square of the distance increases, the magnitude of the electrostatic force will actually decrease, which is exactly what this is all about. Okay, that's the main point, that the square of the distance and the electrostatic force are actually inversely proportional to each other. Right. Now, here's something that is also very important. Now, if we are saying that the electrostatic force is inversely proportional to the square of the distance, okay, we are also saying that at the same time, the magnitude of the electrostatic force is directly proportional to the reciprocal of the square of the distance. So 1 over r squared is actually directly proportional to F, or F in principle is directly proportional to the reciprocal of the square of the distance between the charges. Hence, we get that linear graph. So when 1 over r squared increases, then the force will also increase. So this is the main idea in as far as, the distance as well as the product of charges, and as far as the Coulombs law is concerned, right? Now, this is what it's all about. This is what it all boils down to, because we were so concerned about the Coulombs law and what exactly it means when we say two quantities are directly proportional while others are inversely proportional. It says here the magnitude of the electrostatic force exerted by 1 point charge Q1 on another is directly proportional, okay, to the product of the charges. So we are saying F, which is the electrostatic force, is directly proportional to Q1 Q2. So this is what we mean when we talk about the product. So the product is the multiplication of the magnitude of the two charges involved, while at the same time we're saying it is inversely proportional to the square of the distance. Take note, square of distance is different from square root. Okay, so that's one of the things that obviously come up. You know, if we talk about the square of the distance, in this case it's r squared, which is totally different from square root. So we need to have a clear distinction in as far as those two are concerned, right? So here, what are we saying? We are saying F, which is the electrostatic force, is inversely proportional to the square of the distance, which gives us at the end, F is proportional to Q1, Q2, right, over R squared. So there are two aspects to the definition of Coulombs law, that of directly proportional as well as inverse proportionality, right? Okay, now let's look at the data sheet, okay? The data sheet is, this is what is going to be given to you as in the formula sheet, okay? So from mathematically looking at that, you can see the product of the charges, you can see the square of the distance. So this is the product of charges, right? So that's the product of the two charges, point charges concerned, and then the square of distance, okay, between the two charges. So that's the square of distance. So which mathematically gives us that Coulombs law, whereby K is that constant, okay? The units Newton meter squared per Coulomb squared. So you need to also be familiar with that and distinguish it from the G, which is the universal gravitational constant, right? Now, in terms of applying the Coulombs law, multiple choice questions have got a special focus on the conceptual understanding of any physics concept, right? So you need to be able to apply the Coulombs law, you know, appropriately based on your understanding. Because after investigating the factors, we've realized that there are two main things that actually affect the magnitude of the electrostatic force. One is the product of the charges, the 2-point charges, okay? And also the square of the distance between the two charges. Now, if we talk of direct proportionality, it has to do with the product, how it affects the electrostatic force. And in both cases, the electrostatic force is always the dependent variable. And then again, here it says as an example, the magnitude of the electrostatic force exerted by 1-point charge, Q1, on another is Q2. So our force is equals to 16 newtons is given, okay, right? Now, what happens to the force when the charge on Q1 is doubled? Now, if we double Q1, it means, in other words, we are saying that the 16 newtons is equals to K, Q1, Q2, whatever Q1 is and Q2 is R squared. The assumption here is that we keep the distance the same. So if we double Q2, we double Q1, we'll have K 2 Q1, right? Q2 over R squared, right? Now, if we're saying this is equal to 16, mathematically left-hand side is equals to right-hand side. So this term on the right-hand side is equals 16. So I want to express the new force in terms of 16, right? This is going to be 2K Q1 Q2 over R squared. So this is like 2 multiplied by 16. So if we double one of the charges, the actual force will be doubled. So the new force will be equals to 32 newtons. So this is what it's all about. That's what it means when you say the product of the charges is that it affects the electrostatic force. So the electrostatic force is directly proportional to the product of the charges. So if we double the product, the electrostatic force will also be equivalently doubled, right? And then the magnitude of the electrostatic force, still the same, 16. What happens to the force when charge Q, both of them are doubled? So in this case, we have got K, 2Q1, we've doubled Q1. 2Q2, we've doubled both charges, we've kept the distance the same. So this is like 4K Q1 Q2 over R squared. Now we know that this is our 16. So this is the new force will actually be 16 multiplied by 4, which is 64 newtons. So as the electrostatic force, as the product increases, so does the magnitude of the electrostatic force. Now, having said that, I think it's proper for us to appreciate that if we understand the concept of what exactly it means when we say that two quantities are directly proportional, how exactly does it affect the other one? So that's the long and short of it. And then last but not least, let's look at a scenario which involves the distance. It says, what happens to the force? Okay, how does it affect the force when the distance is doubled? Okay, so what we know is that 16 is equals to K, Q1, Q2 over R squared. Okay, now we're going to double the distance. So this is our 16. So if we double the distance, it's going to be K, Q1, Q2 over 2R. Now we are squaring 2R, take note of that, okay? So if we square 2R, this reduces to K, Q1, Q2 over 4R squared, okay? So this is like 1 over 4K, Q1, Q2 over R squared. So that's our 16. So the new force will actually be a quarter of the original one. Actually, the force has actually decreased because we've doubled the distance. That's the inverse proportionality. So the new force will be a quarter of 16, which is actually 4 newtons, right? So this is how exactly we apply these. But the main thing, again, that we also need to take into account is the fact that whatever force charge 1 exerts on charge 2, it's equal in magnitude to that exerted by charge 2 on charge 1, but opposite in direction. Now, we're onto something. It obviously takes us to the Newton's third law, right? The forces are equal in magnitude, but opposite in direction. So that's as far as, the factors that affect, the magnitude of the electrostatic force in terms of distance and the product of the charges. Having said that, hopefully this has made a lot of sense in terms of trying to unpack the Coulombs law. And because of time constraints, we've reached the end of our session today. From myself, Themba Ncube, is cheers and bye-bye for now.